Today we'll talk a little bit about tangents to polar curves. And just as a reminder, a polar curve is defined in this form, r equals f of theta. So where the radius, which is the distance from the pole, depends on the angle that you're rotating through. We call the pole, the origin basically is the pole. And then generally we just draw a ray to the right. And this thing is the polar axis. And so we learned last week how to graph certain functions. First we learned how to graph polar coordinates, r comma theta. So you rotate to angle theta, and then you go out a distance of r from the pole. And there is your point r theta. All right, and then we graphed a couple polar curves. So let's talk about tangents to polar curves. All right, so we can convert using basically our formulas from last time. I'm going to get all this writing off the page. We can convert, let's go convert polar coordinates to Cartesian, right? And we just do that by saying, well, the x-coordinate is r cosine theta, and the y-coordinate is r sine theta. Right? So if you need a reminder about why that is, if this is my coordinate plane, and I have this polar coordinate r comma theta there, then that's theta, and I can make a right triangle out of that, where this is the x distance and this is the y distance. That's r. And so once again, we know that cosine of theta is x over r adjacent over hypotenuse. Multiplying by r, we get that x equals r cosine theta. And then we can do a similar setup for the y-coordinate. Y equals r sine theta. Well, it's already understood, right, that polar functions have the form r equals f of theta. So all I'm going to do is replace my r here with f of theta, and here with f of theta. So now I have x equals f of theta times cosine theta, and y equals f of theta times sine theta. And so now that's a set of parametric equations. With theta as the parameter. All right, and what we did the entire last section was learn how to do calculus with parametric equations. So specifically, we know that the derivative of a parametric curve is dy d theta over dx d theta, right? So let's kind of try and figure out what this is going to be. So with dy d theta, I'll do this off to the side. We're trying to take the derivative d d theta of f of theta times sine theta. All right, you guys remember Calc 1? What rule am I going to have to use to differentiate that?
Product rule.
Yep, product rule. So that's going to be, I can go f prime of theta times sine of theta plus f of theta times cosine of theta. All right, and then for dx d theta, again, we're going to have to use product rule, so f prime of theta times cosine theta minus f of theta times sine theta. Hey, remember that f is the same as r. So another way of thinking of f prime is that's dr d theta. So I could write this final answer if I like as dr d theta sine theta plus r cosine theta over dr d theta cosine theta minus r sine theta. One kind of interesting thing here, so I'll make a little note. So if we're looking for a tangent specifically at the pole, then the radius is 0. And if the radius is 0, these terms are going to go away. And you can divide out the dr d theta. And we just end up with sine over cosine, which is tangent of theta. So it's interesting because a derivative is a slope of a tangent, and in this case, a derivative. The derivative is tangent of theta. Alex, I'm sorry, what's the question? F prime. Is that dx d0? The angle.
Oh wait, I just realized that you did it in reverse. I thought you would do it. Never mind.
Okay.
I thought never mind.
Okay.
Never mind.
All right. Anyway, so the big takeaway, this is our general formula for finding the derivative of a polar curve. All right. Okay. So I'm going to skip that. Let's just get to an example. For the cardioid, r equals 1 plus sine theta, find the slope of the tangent line when theta equals pi over 3. So again, really what we want to do first is just convert this to a parametric form. So x equals r cosine theta, whoops, y equals r sine theta. So in this case, x equals 1 plus sine theta times cosine theta. And then y equals one plus sine theta times sine theta. All right, and so what we want is basically dy dx at theta equals pi over 3. So first let's find dy dx. All right, so for dy d theta, we'll go ahead and use the product rule. And I'll go derivative of that inside is just cosine theta. And I'll have times sine theta plus, and derivative of the other term, 1 plus sine theta times cosine theta. Over dx d theta. Okay, you get cosine theta times cosine theta. And this is going to end up being minus 1 plus sine theta times sine theta, because the derivative of cosine is negative sine. All right, well, if I were just finding this as a function, I would probably try and simplify it a little bit, but I just want the derivative, the actual value of the derivative at pi over 3. So I'm just going to go ahead and plug in pi over 3 for all my thetas. And it's important to remember off to the side, because I'm going to find an exact answer. Pi over 3 is what? 60 degrees? So we are talking about a 30, 60, 90 triangle here. So we'll call this 60 and this is 30. Across from 30 is 1. Hypotenuse is 2. Across from 60 is rad 3. And we're going to be focused on finding trig values of that 60-degree angle. All right, so I have what? Cosine pi over 3 times sine pi over 3 plus 1 plus sine pi over 3 times cosine pi over 3 over cosine pi over 3 times cosine pi over 3 minus 1 plus sine pi over 3 times sine pi over 3. All right, well, let's make a note, because it's basically just a bunch of cosines and sines. So cosine of pi over 3 is going to be cosine of 60, which is 1/2, right? Sine pi over 3 is going to be root 3 over 2. Okay. So what I have is what? 1/2 times root 3 over 2 plus 1 plus root 3 over 2 times 1/2 over 1/2 times 1/2 minus 1 plus root 3 over 2 times root 3 over 2. Oh, I'm running out of space here. All right, root 3 over 4 plus 1/2 plus root 3 over 4 over 1/4 minus root 3 over 2 minus 3 over 4. All right, I need to simplify this a little bit more. I need some space. All right, I'm going up here. So we have 1 half plus 2 root 3 over 4 over negative 2/4 minus root 3 over 2. That becomes a 2. That becomes 1 half. Okay, let's go ahead and flip and multiply. 1 plus root 3 over 2 times 2 over, I can factor out a negative 1. 1 plus root 3. Well, everything's going to cancel. Whoops. And I'm going to be left with negative 1. All right. So what we've said is this. dy dx at theta equals pi over 3 equals negative 1, right? And just to check that this is true, I'm going to find the full-on equation of the tangent to that point. But before I can do that, remember that x equals 1 plus sine theta times cosine theta, and y equals 1 plus sine theta times sine theta. So to be able to write the equation of a tangent line, I need a point, the point of tangency, and I need the slope. Right now I know the slope, I just need the point of tangency. I need the Cartesian coordinate xy. And so I can just plug in my value of theta, pi over 3, to my x and my y parametric equations here. So at theta equals pi over 3, x will be 1 plus sine of pi over 3, that's root 3 over 2, times cosine of pi over 3, so times 1 half, and y equals 1 plus root 3 over 2 times root 3 over 2. All right, so that x coordinate is 1 half plus root 3 over 4. The y coordinate is 3 over 4 plus root 3 over 2. Okay, and I'm doing that because I want to go in my calculator and actually I want to show you in Geogebra, so give it 1 second here. The point we were looking at was 1 half plus square root of 3 over 4, comma, and then I said 3/4 plus square root of 3 over 2. There we go. And you can see that is on the curve. And so if we got the correct slope, we should be able to see the equation of this tangent line that goes through that point. And so the equation of the tangent line would be, it's going to be kind of messy because we don't have super nice coordinates, but it would be y minus the y coordinate, so y minus the 3/4 plus root 3 over 2 equals our slope times x minus the x coordinate, so x minus the 1/2 plus root 3 over 4. All right, so let's see if that does it. Okay, so y minus, what's happening here? Y, come on. Y minus 3 over 4 plus square root 3 over 2 equals -1 times x minus 1/2 plus square root of 3 over 4. Boom. There we go. It is tangent at that point. So that's at the angle pi over 3. There we go. All right, find the points on the cardioid where the tangent line is horizontal or vertical. So you will get a horizontal tangent when the numerator is 0. So that's when dy d theta equals 0. So let's just do that. So dy d theta, again, using the product rule, would be cosine theta times sine theta plus 1 plus sine theta times cosine theta. I'm going to set these equal to 0, set this function equal to 0. And we're just going to try and solve for values of theta. All right, well, notice that I have a cosine factor in both terms here, so I'm going to factor that out. So cosine theta times sine theta plus 1 plus sine theta is 0. So they're separately factored or separately able to be factored and set equal to 0. So cosine theta equals 0, and this one's going to be what? 2 sine theta plus 1 is 0. Isolate the sine, so sine theta is -1/2. All right, so we're trying to figure out values of theta that would solve these equations. And so we can kind of just do this by inspection. You have to remember some things about the coordinate plane and the unit circle, but basically there's going to be infinitely many solutions to this. So when is cosine 0? Well, remember that on the unit circle it goes cosine theta comma sine theta. So cosine is the x coordinate. So we're going to get 0 values of cosine here and here for any coterminal angle of those, right? All right, so the first value is going to be pi over 2. And if I'm just going through one rotation of the circle of the cardioid, then 3 pi over 2. But really, any value that's coterminal with those are going to get me also horizontal tangents, right? All right, and then when does sine theta equal -1/2? Well, the only triangle that gives us a ratio of 1/2 is that 30, 60, 90 triangle. If this is 30 and this is 60, that's 2, that's 1, that's rad 3. So if you focus on, you want sine to give you a ratio of 1/2, then this is opposite and the over the hypotenuse is 2, right? So 30 degrees is what? Pi over 6. But we don't want a positive ratio of 1/2. We want a negative ratio of 1/2. So we have to think about what quadrants is sine going to be negative in. And this is where that acronym can sometimes help you. I don't know if Kenton does this acronym with you, but it's all students take calculus. And that just tells you what trig functions are positive in each of the quadrants. So in the first quadrant, all trig functions are positive. In the second quadrant, sine is positive and the other two are negative. So if we want sine to be negative, we're going to look for that angle to be in the third and fourth quadrants. So I need this to be an angle of pi over 6. Oops, pi over 6. And I need this to be an angle of pi over 6. So those are just the reference angles. The true angles are measured from here. So what's that green angle if that reference angle is pi over 6? Help me out here. Let me know that you're alive. I want to know the complete angle from here to my reference angle of pi over 6.
Is that one 7 pi over 6?
It is. It's just pi plus pi over 6, which is 7 pi over 6. And then what's the last angle? So that would be from here all the way around to here. So for that one, you can just take 2 pi and subtract off pi over 6.
11 pi over 6?
Yes. Okay, those are the values of theta where our cardioid has a horizontal tangent. But if I ask you to, on the test, find the points where the cardioid has a horizontal tangent, that means you need to find me the xy Cartesian coordinates where that's the case, right? And so if I wanted to do that, I would go for each one of these 4 angles. I'm going to plug that angle back in for theta in both my x and my y. I'm going to simplify and I'll get a value. There's not a lot to this other than it's kind of time consuming because you're just plugging in and simplifying. So I'm just going to give you the answers when we plug in those 4 values of theta. We end up with oh, and I'm sorry, they actually want, so when they say points, they want it in terms of r theta. So not Cartesian, polar, which is fine. Then all we have to do is plug them into one place. We don't have to plug them in for x and y. So my first one, for example, my theta is pi over 2. So when I plug in pi over 2 to my r function, sine of pi over 2 is 1. I get 1 plus 1, which is 2. So in polar form, I have the point 2 comma pi over 2. And then when I plug in 7 pi over 6, I actually end up with 1/2. 11 pi over 6, 1/2. And the last one for horizontal would be which one didn't I do? 3 pi over 2, huh? Ooh, okay, but 3 pi over 2, although it does produce a 0, okay, so I have to point out one more thing. So these are the horizontal tangents. Let's talk about vertical tangents. So these are horizontal. And then over here I'll do vertical. So for vertical tangents, we want to focus on when the denominator is 0. So when dx d theta is 0 for our derivative. And that is to say, that would be cosine theta times cosine theta plus 1 plus sine theta times cosine theta. We're going to set that equal to 0. Oh no, I'm sorry. I didn't take the derivative of the second. This should be minus. I didn't take the derivative of either factor there. So that should be sine theta. And this should be minus. All right, so we have a trig identity that will actually allow us to, let's see, I can replace cosine squared so I can replace cosine squared with 1 minus sine squared. I'll distribute this sine and distribute this negative, and I'll get minus sine theta minus sine squared theta. I'm having that set equal to 0. All right, so I actually have 1 minus sine theta minus 2 sine squared theta equals 0. And so there's 3 terms. So this is functionally just like a trinomial. And this one's actually factorable, right? It factors to 1 plus sine theta times 1 minus 2 sine theta. If that's confusing, just replace the sine thetas with x's momentarily, and you see that you have 1 minus x minus 2x squared. And that can factor out just using algebra 2 sort of logic. All right, so then we end up with, just separate those factors. So I get 1 plus sine theta equals 0. And I get 1 minus 2 sine theta equals 0. And so this is going to give me sine theta equals negative 1. And sine theta equals positive 1/2. All right, well, we already saw when sine has a ratio of 1/2, we did this in the last part of this problem. That's going to be for angles that are coterminal that have reference angles pi/6. So one of them is pi/6. So one solution to this is theta equals pi/6. And that's in the first quadrant. And then the other one is going to be whatever this angle is, which is what? Pi minus pi/6. So 6 pi/6 minus 5 pi/6. 6 pi/6 minus pi/6 is 5 pi/6. Okay? And then remember, we would end up with negative values of -1/2 if we looked at the angles in those two bottom quadrants. So we don't need to look at those. We only want the +1/2, the angles that give us a ratio of +1/2. Okay, so we're done with this one. Now we need to focus on, okay, when is sine of theta -1? Well, if we think about the unit circle, sine being the y-coordinate, the y-coordinate is -1 here. That angle is 3 pi/2. All right. So we're ready to write out the coordinates of our vertical slopes. First one, let's plug in pi/6. We're going to end up with a radius of plugging pi/6 into sine theta and simplifying. We get 1 + 1/2, which is 3/2. All right, plugging in 5 pi/6. We're also going to get 3/2. Now 3 pi/2 is interesting because it made our dx d theta 0, but it also made our dy d theta 0. So really, 3 pi/2 makes this an indeterminate form, 0/0. And you can technically at that point then use L'Hopital's rule. So you take the derivative again of the numerator, take the derivative of the denominator, and then plug in 3 pi/2. What you end up seeing, though, is that 3 pi/2 does give you, after you use L'Hopital's rule, it will give you a vertical asymptote. And I'm not going to go through those steps just because I think we've spent enough time on this problem. But we'll see graphically that this is the case. So when we plug in 3 pi/2, my radius is actually 0. So we are actually at the pole there. And that's just because of the shape of our cardioid. So I want to go through on our calculator and practice graphing this. So I'm just going to change my mode to polar. We're going to graph 1 plus sine theta. We're going to go to our window. We just need a full rotation here, and there's nothing crazy going on with our angle. Like there's not an angle multiplier that would change the period. So we really only need to go from 0 to 2 pi. I'm going to keep my theta step pretty small, 0.01. And then let's think of our actual viewing window. How far do I really need to see out here? I think the biggest our radius ever got was 2, so I'm going to go like just negative 2.5 in every direction, or in all 4 directions. Go ahead and graph it. Again, it looks a little distorted because it's in a rectangular mode. If I do the zoom square, zoom 5, there we go. Get kind of a better image of our cardioid. All right, I think I should be able to give it some polar coordinates. So let's see. Our horizontals were at 2 comma pi over 2. So if I do 2, no, if I do theta is pi over 2. There we go. You can see that my cursor is now on, it's clearly going to be a horizontal tangent there. Where else? We had 2 others. We had when theta is 7 pi over 6, so 7 pi over 6. Okay, you can see a horizontal tangent at the base on the left-hand side of the cardioid. And then you're going to expect probably that last point is going to be on the right-hand side of that cardioid, that horizontal tangent right there, and that's 11 pi over 6. And it's going to give me a radius of 1/2. Oh, you know what? It doesn't even spit back the radius. It gives me the Cartesian coordinates there. That's funny. But it is a radius of 1/2 right there. All right, and then we had these vertical tangents, right? So we had a vertical tangent, and you can kind of take a guess at where you think the vertical tangents are going to show up on this cardioid, right? You're going to have one on the far right. You're going to have one on the far left. And then you can see we approach a vertical tangent at the pole because you get that sort of spine in the middle, right? All right, so let's just make sure that that's the case. So we have one at pi over 6. There you go. And that's clearly a vertical tangent. We have one at 5 pi over 6. There you go. And then our last one is at 3 pi over 2. And that's right there at the pole where we get that spike that creates a vertical tangent. All right. So there's the book's visualization of it. It's funny because they give, and this one is our, from part A when we found the tangent at that point. They give every point in here in polar coordinates except the pole. They write in Cartesian form. All right. So we need to know how to sketch polar curves by hand, or like the general idea of that. But it's also useful to be able to sketch them using computers and calculators. But some of these, it's hard to know how do you figure out what parameters to give your angle theta so that you are graphing the entire curve, okay? So when we're looking at curves like this that have something going on with the angle, that multiplier is actually going to change the period of the function, and it's also going to change what the function looks like, or how long it takes to fully rotate through before it begins tracing back over itself. So we want to be able to have a way to figure out what the domain of theta is such that we will trace out our entire curve, okay? So one way you can do this is convert to parametric like we did, and that's kind of how I graphed it in Geogebra. But you actually don't need to do this. Your calculators can graph in polar form, as we've already seen. But now we're going to talk about the appropriate domain for theta such that the entire curve is traced out. And let's show you why. So let's just plug in 8 theta over pi for R1 in our calculator. And let's just graph it with the current parameters that we have on theta. So sorry, that was sine 8 theta over 5. And so if I graph it where I'm just taking theta to go from 0 to 2 pi, and actually let me get us, oh, that's not good. So I'm just going out 3 in all 4 directions. But here's where I get a few loops. But I'm clearly not getting the whole graph. All right, what if I continued? What if we went to like 4 pi? Okay, I'm getting more of it, but it's still clearly not the whole graph. I'm kind of stopping short. So I want to see what's a better method other than just guessing and checking to figure out the domain of theta so that you're actually tracing out the full graph. All right, so I'm going to let n be the number of complete rotations it takes before the curve repeats, meaning traces over itself. So then, at that point, the output you get I'm going to say sine of 8 times theta plus 2n pi over 5 will just give me back my original output. It'll be the same as sine of 8 theta over 5. So the reason it's 2n pi is, remember, we're considering n to be a number of rotations, right? So how many radians are there in a complete rotation? There are 2 pi. So however many complete rotations, we're going to multiply that by 2 pi. We're going to add that to our input angle. And then we're going to set it equal to the original output. And what we want to figure out is the first value of n that would make this occur. So I'm going to kind of simplify what I have on the left-hand side there. So I'm going to distribute the 8, and I'm going to go, okay. So sine of 8 theta plus 16 n pi, that's over 5. And I need that to equal sine of 8 theta over 5. And then I can split up this fraction on the left. I'll rewrite it as 8 theta over 5 plus 16 pi over 5 times n. And I need that to be equal to sine of 8 theta over 5. Okay. So here's what I want you to think about. The first time these two things will be equal will be when this term is an even multiple of pi. Meaning it has to be the first time that that is a multiple of 2 pi. Because if you add 2 pi to any angle, right, you just get back to a coterminal spot in that angle. So if this is the angle I'm talking about, if I add 2 pi to that angle, I'm back here. And then sine of that angle is going to be the exact same, right? So I need 16 pi over 5 times n to be an even multiple of pi. So my question to you is, what is the first value of n to make this occur? So remember a couple of things. N has to be a whole number because it represents a number of complete rotations. And in this case, we want to figure out the first value of n that will make 16 pi over 5 times n an even multiple of pi. Okay, well, we can just try values of n, and then we can look at values of 16 pi over 5 times n. So if I do 1, then I get 16 pi over 5. That's definitely not an even multiple of pi, right? If I do 2, I get 32 pi over 5. Still not an even multiple of pi. 3, 48 pi over 5. Still not an even multiple of pi. 4, 64 pi over 5. Still not an even multiple of 5. 5. That's going to simplify to 16 pi, right? So when n equals 5, that's the number of rotations it takes before the curve starts to trace back over itself. So n equals 5. 5 complete rotations. In radians, how much is 5 complete rotations?
Two pi.
1 rotation is 2 pi. How much is 5?
10 pi.
Okay, there's our domain. If you let theta go between 0 and 10 pi, we should get the graph completely traced out and stopping before it traces back over itself. So I'll just go to my window. I'll change my theta max to 10 pi. Sweet. And so now, here, I'm going to try and make my theta step really small so it'll take a minute to graph this. So this is called a 16-petaled rose. You can see if I increase it at all, if I increase my theta to be bigger than 10 pi, if I go 11 pi, you're not going to see any difference because it's just going to now be tracing back on top of one of the loops that it's already traced out. So it was still going for a little while after, but you couldn't tell the difference because it was actually just tracing over part of the graph that it had already graphed. All right.